Substitution and elimination are effective tools for solving simple systems. However, as variables multiply, we require the systematic structure of the matrix method. A transport fleet operating on this highway manages dozens of variables simultaneously: fuel consumption, toll fees, driver wages, and cargo weights for every vehicle. The matrix method converts this entire logistics network into a standardized grid, allowing software to calculate the optimal path for all 50 variables in microseconds. This is the logic used by professional engineering and accounting software to process immense datasets without the risk of manual arithmetic errors. We can see this structure in a standard market transaction. At Jinja Central Market, one customer buys 2 notebooks and 3 pens for 5,000 shillings. Another buys 4 notebooks and 1 pen for 4,000 shillings. These transactions form 2 linear equations. Here, X represents the price of a notebook, and Y represents the price of a pen, with the total costs aligned on the right. To solve this, we extract the data into 3 specific matrices. The coefficients forming the notebook and pen quantities become matrix A. Our unknowns form the variable matrix X, and the totals become our constant matrix B. This organization translates the market transactions into the standardized formula A times X equals B. Our objective is to determine the values inside matrix X. Because matrix division does not exist, we cannot simply divide both sides of the equation by A. To isolate our variables, we multiply both sides of the equation by the inverse of matrix A. This cancels the coefficient matrix on the left, leaving us with the solving formula, X equals A inverse times B. Let's apply this logic to a new set of equations, 2x plus 3y equals 8 and x plus 2y equals 5. First, we convert the system into its matrix components. We align the coefficients 2, 3, 1, and 2 into matrix A, and place the constants 8 and 5 into matrix B. Properly structuring these matrices is the necessary prerequisite for any further arithmetic. We begin by finding the determinant for matrix A. This involves cross-multiplying the diagonals, 2 times 2 minus 3 times 1. In this case, our determinant is 1. We then construct the inverse matrix by swapping the positions of the main diagonal and reversing the signs of the remaining values. Because our determinant was 1, the values inside the matrix remain whole numbers. When preparing the final multiplication, we must observe the requirements of matrix algebra. Unlike standard multiplication, the sequence of these components determines the result. The inverse matrix must be positioned to the left of the constant matrix. If the order is reversed to B times A inverse, the dimensions of the matrices will not align, and the calculation becomes impossible. Maintaining the order of A inverse times B ensures the rows and columns are correctly oriented for the final step. Pause the video here and perform the multiplication yourself. Multiply the 2 by 2 inverse matrix by the constant vector of 8 and 5. Let's process the calculation. We multiply the top row of the inverse by the constants to get 16 minus 15. We then repeat the process for the second row. The final resulting vector contains the numbers 1 and 2. These results correspond directly to our unknowns, x equals 1 and y equals 2. On a coordinate plane, these values represent the exact point where 2 lines cross. By using matrices, we have found the single coordinate that satisfies both equations simultaneously. This geometric relationship explains what occurs when a determinant equals 0. Here, the second equation is a multiple of the first. The determinant calculation, 12 minus 12, equals 0. Geometrically, this means lines are perfectly overlapping. With no single crossing point, no unique solution exists. The matrix method is designed to fail at this step, providing a clear indication that the system lacks a single intersection. To solve any system using this method, organize your equations into the AXB format, verify the determinant, and apply the multiplication of A inverse times B. To access comprehensive courses and practice problems for all classes, visit the Yaka Digital Network at yaka.cc. Mastering these steps transforms basic algebra into a tool capable of solving the complex systems found in the modern world.